So we are in Statistical Rethinking, second edition. We're in Chapter 9, and we're in the easy questions, and we're on 9E2. Okay. So this chapter is all about these algorithms to solve Bayesian models or Bayesian probabilities. And previously we looked at the Metropolis algorithm, all right? And this question is about the Gibbs algorithm. So this book is not very big on the details, and that's fine because a lot of these approaches, such as Metropolis and Gibbs, really are more or less obsolete once you start to use something like Markov chain Monte Carlo. But they're good to know about anyway. So if you want more detail in a way that's kind of approachable still, I again suggest you go to this book. I think this takes you to an Amazon link. I don't get anything from it, but it's a good book, A Student's Guide to Bayesian Statistics by Ben Lambert. And there's a little bit more detail in there about some of these algorithms. So, okay, so here's the question. So Gibbs sampling is more efficient than the Metropolis algorithm, which we saw in the first question. How does it achieve this extra efficiency, and are there limitations to the Gibbs sampling strategy? Okay, well, we need to know a little bit about Gibbs in order to be able to answer any of this. So Gibbs is just another sampling algorithm, and it is in fact generally more efficient than the Metropolis algorithm. Okay, now the way that it does this, and we'll go through an example in a moment, but the way that it does this is, first of all, it really only does really well when it has more than one parameter, so more than or equal to 2 parameters. Okay? And the way that it's doing this is that it's trying to suss out the relationship between the parameters, say theta A and theta B or something like that. Okay? And so as it starts to map the posterior space, the parameter space, it also starts to delineate the relationship among the parameters. Okay, and as it starts to understand the relationship among the parameters, it can make better and better proposals going forward, right? Because if I know a lot about all of the parameters to which parameter A is related, well, then I can tell you quite a bit about parameter A and where it might be. Okay, so hopefully that makes a little bit of sense. So let's go through an example here, just using 2 parameters. Okay, so say we have some data y and 2 parameters, theta 1, and it's distributed in some way that we can define, and theta 2 that is distributed in some way we can find, or these are prior probability distributions. Okay? So the first thing we do is we just start by generating random values from their respective prior distributions for theta 1 and theta 2. So if I come down here, so here I have my parameter space, okay, and I see what my true posterior is right here, but again, we don't see that. We don't know that. We're trying to estimate that. And the first thing I do is I just randomly pick theta 1 and theta 2 from their prior distributions, and I plot it right there. Okay. So now we have to pick one of the 2 parameters to update theta 1 or theta 2, and we're going to do it conditional on the other parameter. Okay. So I'm going to use the probability distribution for the first draw of theta 1. Oops, there shouldn't be a comma there. But given that theta 2 is at its not value and y, right? So I have a probability statement that I'm trying to work out here, okay? That will lead me to a proposed value for theta 1 for the first draw of theta 1. Okay, and so then I'm going to plot that. Okay, notice that the value for theta 2 has not changed. It's still at the same level. Okay, so now having a proposed value, so I always accept. In fact, that's why the Gibbs is more efficient. Is I'm always accepting the proposal. Right? There's no accept reject. I'm always accepting. Okay? So now I have a value for theta 1. Or one value for theta 1, and so now I'm going to propose and accept automatically a value for theta 2 to go from theta 2 naught to theta 2 1, And the way I'm going to do that is I'm going to draw from, again, this conditional probability here, the probability of theta 2 for the first actual draw, given that theta 1 and its first draw and the data. And that brings me to some value here that was, again, based on a probability distribution. It's not deterministic. You know, this value could have been up here or down here. It just happened to land here given that probability. Okay. So now I have new values for theta 1 and theta 2, and I'm just going to repeat this. So now I'm going to go to, now I want to make another proposal and automatically accept theta 1. So I have a probability distribution for the second draw of theta 1 given theta 2 and its first draw and data. And I go here. And this process that just continues and continues and continues. And again, as each data point is found, the algorithm begins to suss out the relationship between theta 1 and theta 2. And so, you know, given the posterior here, we see that they're positively correlated, and that will be detected. And the samples will increasingly map out and focus on the posterior distribution here. Okay. So that's great. So now we're also asked about any limitations that the Gibbs sampling strategy has, and there is. And the major limitation here, I guess there's a couple. One is if the parameters are really highly related, then you can then Gibbs can kind of get stuck because so imagine that this posterior distribution didn't have any width here; it was just a straight line. Well, then it becomes incredibly confined, and so the Gibbs sampler can kind of stall out on some part on that line. But ignoring that, because we could reparameterize the model, I think, and it could be okay, or it's possible we could reparameterize the model and be okay. But the other problem is that these little computations right here, as I go from point to point to point, these can be really, really hard to do. And so it requires that our chosen probability distributions, our priors, are what are called conjugate priors, okay? And so this book doesn't talk much about conjugate priors, but I guess all that's important about conjugate priors here is that a conjugate prior is a type of prior that multiplies very nicely with the likelihood, right? So that you get a tractable solution to as you're running Bayes' theorem, or at least estimating as you're calculating Bayes' theorem. But the problem is that often we want priors that don't multiply nicely with the likelihood. Okay, so a conjugate prior makes it possible for you to do Bayesian analysis just with pen and paper, but that is also a limitation, right? Because we can't. A lot of times we want priors that don't play nicely with the likelihood. Okay, so in which case Gibbs becomes not very helpful. Okay, so that is it for this one, and I'll see you next time.